the overall theme is this mechanics-based design for computational fabrication, where the goal is to find these connections between principles of physics and how that can be embedded into geometric modeling pipelines for design. So as everyone here is very aware, there's been this huge resurgence of rapid prototyping methods and rapid manufacturing, where techniques have become much more accessible, both economically and at different scales, in terms of the materials that can be produced through, say, commodity 3D printers, material properties that can be played with, increasing levels of accuracy. And as a result of that, we're seeing applications across a huge set of different domains. So artistic explorations, medical applications, industrial products. So it's really wonderful to be seeing these broad range of applications in customization for design and fabrication. So what my lab focuses on, however, is that there's still this remaining bottleneck where when we're looking at the complete pipeline, not just in the accessibility of the hardware, but the full pipeline from conception of an idea through to its manufacture to get the physical product, that we're thinking about functional objects, there's actually a lot of different considerations that go into the functionality conditions. So properties such as stress analysis, like loading, the prosthetic example here is a perfect example of that. Strength to weight ratios that are needed, say, for wearable devices and products. So this type of functional design is still within the realm, you might say, of experts in understanding the tools that are involved in both the geometric modeling aspect, as well as assessing and understanding the functionality constraints. So what I'm interested in is how to open this up and create computational methods that can embed functionality needs into the design pipeline to increase their accessibility. So that's the idea behind this mechanics-based design for computational fabrication, where we're trying to create these unified methods that combine principles of mechanics with computational methods in geometry processing. So there's three main components shown in this triangle graphic, where the main components are first the mechanics, so predicting and controlling mechanical properties, pairing that with geometry processing, so manipulating complex 3D geometric models. And then finally, of course, the fabrication aspect, where you can create the physical prototype, observe those functional behaviors, and potentially also create new methods of making and building. So we've explored this combination of functionality, mechanics, and geometry in a number of different examples. One area is within architectural geometry. So in architecture, a classic example of where you have this intrinsic link between structural mechanics and geometric design. We looked into examples such as using procedural rules. So this is a hierarchical method of defining an architectural style that can be done sort of grammatically. And we looked at ways in which properties of feasibility, so that you actually have, say, structural static equilibrium, that can be embedded into the rules, so that everything you create is actually a feasible structural building. Another example domain is in going down in scale to the stability of 3D prints. So how we can look at different mass properties that are embedded in the design. So some examples are, say, in static equilibrium, very basic property, but you can create objects with surprising balance properties by understanding how to manipulate the mass, or properties of buoyancy, so how an object might float, and also things like rotational dynamics. There's a few different examples. Another fundamental property that's often very important is the rigidity of 3D prints. So there are some examples where rigidity is highly critical. So say in orthopedic casts where you're protecting a fracture site. On the other hand, you might have examples where you want large deformations, but only in particular areas, say for the articulation of an object. So we looked at ways of manipulating the shell thickness to get more or less deformation. or looking at assemblages of objects. So if you have multiple parts and there's tolerances between those parts, you may be introducing a small amount of flexibility in the overall assemblage. So understanding the relationship between those tolerances and that level of flexibility. And then within mechanics, it's not just limited to mass properties in structural mechanics, but other ideas such as acoustics, which could play into the design of wind instruments. Another example with support structures in 3D prints, a common limitation is that when the structural supports, or sorry, support structures are removed, they leave behind small artifacts, often just small residual amounts of material on the surface, which can degrade the quality. So we're looking at ways that we can understand perceptual quality. So what are perceptually important parts of the model? And if we could prioritize that for where supports are placed or not placed. And interaction examples, where the interaction between the user and the object is highly dynamic and critical to the functionality. So one example of that was in rock climbing. So we looked at a way to replicate outdoor routes on an indoor gym so that rock climbers could train on challenging outdoor sites, even when they were far away from that location. Or using different types of filament in 3D printing. So if you use conductive filament, how that could be integrated into interactive devices where touching pieces can act as a button for, say, giving you audio feedback. So this is part of the tangible circuits work that's coming out in a couple months at CHI in 2020. And as a last area, also looking into different ways of creating new fabrication processes. So architectural scale, where you have assemblages of discrete blocks, or casting and molding techniques, or even creating paintings, say, with watercolor, and how that can be done through non-traditional techniques to make that more accessible to people who don't have an artistic background. So that's sort of an overview of the different sort of domains of where we try to find connections in accessibility of computational fabrication techniques. And what I'd like to do is, over the next 20 minutes or so, highlight 4 different projects that are representative of these areas. So this first project that I want to highlight is looking at this aspect of acoustics as a fundamental property in mechanics. So this is work that was presented at SIGGRAPH Asia in 2016. And actually, 2 of the authors, Nobuyuki Matami and Brian Schmidt, were at the time researchers at the Toronto office for Autodesk. And the other authors were Athena Panatopoulou and myself. So the current affiliations are University of Tokyo, Gradient Space, and Boston University. So the idea behind this project was to allow custom design of 3D printed woodwind instruments. So the user could input an arbitrary 3-dimensional shape. So we have the Stanford bunny here. Based on that 3D input, we create an internal cavity just by an offset surface, and that creates the resonator cavity on the interior. And then the user can experiment with different ways of adding the interactive parts. So they can place the mouthpiece where the wind is going to, where the air is going to be blown in, and the finger holes. That can be based on, say, properties of ergonomics. And as they're doing these different manipulations, we give feedback at interactive rates to tell them, oh, these are the notes that are going to be produced from this instrument. And this is done by understanding these properties of acoustics and having a simulation that's running behind the scenes to give that very quick feedback. Then in the end, we output a 3D printable model so they can create this instrument that's playable. And the idea here was that it's actually quite robust and works even for low-grade commercial 3D printers. So here's an example. So the fun part about this is that because you have this big level of customization, you can create these thematic instruments. You can create instruments that are specifically designed for a particular piece that you want to perform. So here the theme is obvious. And we're using 8 different tones with 4 different finger holes in this case. So we are looking specifically at a type of wind instrument that uses a Fipple-based mouthpiece. So what that means is within the mouthpiece, there's a bladed edge. And as you blow air into the mouthpiece, as the air travels over the bladed edge, it creates turbulence patterns, which creates different ranges of frequencies. And the frequency that matches the resonance frequency of the interior resonator cavity is the one that is amplified and creates the tone that you hear. So this is an example of, for this particular ocarina, this is the spectrum response. And what the note produced corresponds to the fundamental resonant frequency. So that's the lowest and largest amplitude here. So we're looking only at that fundamental resonance. And that's an important distinction. It made the problem more tractable. To look at the entire frequency response would also be interesting. That's what you might hear as the term timbre, the quality of the sound, the difference between, say, a note being produced by a piano versus voice. But the note that you identify is characterized by that fundamental resonance. So we used the well-known Helmholtz equation for modeling that acoustic simulation. And the basic idea here is that you have an incident pressure, F, so that's the air that's being blown in, causing pressure on the interior of that cavity. And then you have a reflected pressure that's causing the audible sound. And you have this characteristic matrix A that's giving you that relationship. So it's modeling how these sound waves propagate, relationship between the input and the output. So we needed to be able to use this equation to quickly give feedback on what that resonance is going to be. So in the paper, we go into some detail about how this is done at interactive rates. The main thing here is that you want to find a maximal relationship between the output and the input. This can be solved as an eigenvalue problem. And if you're interested in learning about that, please, I encourage you to go and read the paper. So I'll show you just what we were able to produce. Here we have a screenshot of the design interface. So you can see the input 3-dimensional model. Here we have the Fipple mouthpiece, this red element, and then a single finger hole has been placed. And then down here, you can see along this bottom bar, we've shown for a different configuration. So in this case, the one hole can either be open or closed, and it shows you where along the scale it's going to produce a note. So you're going to get approximately a G for closed and C for open. And that is, that feedback is given through our sound simulation. And the user can add a number of more finger holes with different configurations. So you can see a number of different permutations for opening and closing different holes. And again, a mapping to what note is going to be produced from that configuration. So this is a manual method of experimenting with different hole positions and seeing what that feedback is and then manipulating it to get whatever desired set of notes you want. There is also some level of auto-tuning. We show that you can also provide a mapping between where the actual simulated frequency is and where you'd like it to be, so a target. And by doing some sensitivity analysis of changing the size of the holes, we can also do some automatic manipulation to try to meet the target. So here we have another example. So another thematic design. And this last one, and this is the lead author, Nobuyuki, playing. To show that we can get a range of low tones and high tones. Also, it can be noted that there is a known relationship between like the scaling of the instrument and how it affects the tone, so that can also be changed automatically. All right. So that's an overview of one example where we had a creative design goal of creating these customized musical instruments, and it depends heavily on an understanding of the mechanics of the procedure. Another example of a creative design goal in this next project is where we were looking at the property of spinability. So we were creating objects that had certain rotational dynamic properties. So this project was presented at SIGGRAPH in 2014. The authors are Moritz Baker, myself, Bernd Bickel, and Olga Sorkin-Hornung. All were at ETH Zurich at the time. So the central property behind looking at spinability is the moment of inertia. So this is a very basic fundamental property of physical objects. And this is central to the functionality of all sorts of industrial products, navigation controllers for airplanes, proper load balancing on rotating parts. But in that same theme of creativity, playability, we were looking at a particular example where moment of inertia comes into play, and this is for spinning tops. This is the toys that we're all very familiar with of how spinning tops get to achieve this almost magical state of balance while they're in motion. And this relies entirely on properties of moment of inertia. So an interesting point historically is that these spinning tops have been part of the toy culture in human civilization since ancient times. So this is an artifact from 480 BC in ancient Greece, where they're actually playing with a spinning top. You can see that on the ground between the two figures. But something that's also notable here is that there's a very similar shape in the spinning top in the artifact and the ones that you see in this modern photograph of the ones you'd find in a toy store today. So I think this helps support the point that understanding intuitively moment of inertia and how to design for it is actually quite difficult. And we haven't really departed from these like rotationally symmetric objects, even though they've been known for thousands of years. So the idea here was to be able to take a more arbitrary asymmetric object and turn that into a spinning top that has the same nice stable spinning properties. It's in slow motion. We have an armadillo spinning on his back. So we achieve this by manipulating the mass of the object. By carving out these hollow regions from the interior, we can change those properties of moment of inertia. So the user specifies what that 3D input shape is going to be, where they want the axis for spinning to be applied, and then we manipulate the mass of the object. So to quickly overview, the basic constraints here are first that you do need static balance. So the center of mass has to lie above that contact point. And then for the moment of inertia, this can be represented with a set of principal axes. And these axes need to be aligned with the spinning axis in order for the rotational dynamics to work out. On top of that, we can also improve the quality of the spin. So there's different ways to make this more stable. The two main ways are, one, to take the center of mass and lower it. So the lower it is to the ground, the more stable it will be. And then additionally, with these principal axes for the moment of inertia, there's a dominant axis, and the larger the magnitude of that dominant axis over the lateral ones, the more stable it will be. So those can be used as metrics in optimizing a shape. So in order to achieve it, we had to find a way to parameterize this hollow or solid parts of the shape to create the spinability. And we did this using voxelization, so splitting the interior into chunks of mass. And this is done hierarchically, so we have different levels of resolution from very coarse to very fine. This makes it also a more tractable problem. And then for each of those chunks of mass, we're finding, is it optimal for it to be hollow or to be solid in order to move toward this spinnable object. So we use an iterative way of slowly refining the sizes of the voxels so we can find a very finely designed boundary between the solid areas and the hollow areas. So here's a photo of a 3D printed version following that optimization. So you can see distinct areas for hollow and solid. And here we have the spinning example. So for this heart model, the arrow is the spinning axis. You can see it's a stable spin. Along the bottom, you can also see how we show the orientation of the principal axes and how the orientation has changed significantly from the input to the optimized result. Right, and here we have the Utah teapot example, first printing it just as a solid teapot to show it doesn't work as is, even though it's close to symmetric. and then following optimization. A big difference in the stability. And then here's the most sort of complex and arbitrary example of an elephant spinning on its toe. So showing this is quite a far departure from the traditional sort of turnip-shaped rotationally symmetric objects. So using this concept of voxelization of the interior and optimizing mass properties over those voxelizations is something that can be applied to different types of mechanical properties. So one other example of that, we also used it for buoyancy. So here, if we have this Stanford bunny model, we can voxelize the interior and manipulate that such that it will float at a particular water level line and also sit upright so its head is out of the water, and also have some stability against perturbation. So even though it rocks around a little bit, it still comes back to a stable position in the end. So that's using very similar techniques. All right, so in those two examples, we're looking at using mechanics for a design application, so something that is sort of a playable output. In these next two projects, I want to show ways that we came up with new methods for constructing or fabricating an object, again, by pairing geometry and mechanics. So this next project was presented at SIGGRAPH this past summer in 2019. The authors are Xiaoting Zhang, Guoxin Fang, Melanie Skouras, Gwenda Giesler, Charlie Wong, and myself, with affiliations at TU Delft, INRIA, and Chinese University of Hong Kong. So with fabric formwork, this is a method for making castings from a mold, where the mold is produced from flexible fabric. So the idea here is that you start off with these 2D fabric panels, and the fabric panels are then sewn together at the seams to create a 3D container. And given that 3D container, you can then use it as a flexible mold, pour in your casting material, which is plaster in this case. And you can see how there's a slight flexing and deforming of the fabric as it's being poured in from that fluid pressure. And then following that, once it dries and cures, you can take away the fabric and you get the solid model in the end. So this is a technique that is nice in that it is very low cost. You have just fabric as your mold material. Here we just used a standard canvas material. It's easily transportable. You can just roll up the canvas and bring it to the site where you want to do the casting. And an interesting aesthetic property is that you have this natural emergence of smooth curved forms. And this happens because of the flexibility of the fabric and how it deforms under that pressure of the fluid and finding that equilibrium. And so this also scales up nicely for larger fabrications. So fabric formwork has been studied quite extensively in the architectural design domain. I'm showing a few examples here of results that have been produced by various studios around the world. So we have some retaining walls, column designs. And I think that what appeals within the architectural domain is this property of the curved forms, organic forms emerging due to the flexibility of the formwork. If you're doing concrete castings using plywood, it's very hard to get these organic shapes without an extreme amount of labor, whereas it's a natural property of these flexible formworks. So a limitation in the past has been that there has not been a complete pipeline where the final shape of the fabric as it deforms under fluid pressure is accurately predicted. So there's a lot of trial and error, understanding how the material behaves by intuition and experience, rather than having a computational pipeline that can say, this is the 3D shape that I want to create. What are the forms that I need to get there? So this was exactly the goal of this project, was to have a target 3D form and to optimize understanding these properties of fluid pressure, of the elasticity of the fabric, and to determine what the shape of those panels should be to get that desired form. So the main thing here was to match the shape properly, to sort of minimize shape deviation. We also were looking at aspects of making it easier to fabricate and also feasible to fabricate. So for example, when you're modifying the panels, the seams have to continue to line up, right? So that's a basic constraint. Also, the seams should be smooth. If you have many jagged boundaries, this can cause problems both in the simulation and also in potentially being a bigger source of error just in the sewing procedure. So there are various factors that we considered. Beyond the shape of the panels, we're also looking at other ways to support the object to expand the range of shapes that could be created. So we had external supports like a string that would hold up pieces, so there's a sort of arched form in that sculpture, and the string is helping to keep it propped up. Cable elements that can be sewn into the fabric provide extra rigidity, and this is important for areas that are locally concave. And also planar supports. So if it's important to have flat regions, which wouldn't normally be possible through the fabric flexible formwork. So the idea here is that we have a big system that has to be operating under force equilibrium. So we have the fluid pressure forces from the cast material. We have membrane forces, so that's within the fabric itself and how it's stretching, and then external forces from these supports. And these all have to balance out to find the final form. The last aspect in designing the formwork was also in how it's actually hung when the casting material is poured in. So if you're considering a simple S shape like this, you can imagine that there's a sphere of different orientations that it could be positioned as it's being cast. If you hang it, for example, from the top, you can see there's going to be quite a lot of deformation in how the S shape behaves under fluid pressure. Alternatively, if you were to rotate it 90 degrees, hang it from the side, there's going to be a lot less deformation. So finding these orientations that reduces these large scale deformations is critical to the process. Otherwise, we'd have to counteract that, say, with adding more external supports. And even small changes in the angle can make a difference in how much deformation you see. So what we're showing here in this stability map is a way to assess for every orientation where the candidates are, so where you'd expect more or less deformation, and then testing out those candidates. All right, so here's some examples of what we produced. So there were string supports and a plane support used here. I'm showing the cast in progress, the fabric being pulled away to reveal the final plaster model. Here, a chair model where plane supports were used to get flat surfaces for the seat in the back. A table model, or use a plane support underneath the surface of the table to reduce sagging. And a simple duck model. Here, the cable support was around the neck to produce that locally concave area. In this last star model, this required several external supports due to the concavities of the angles of the star's points, but we were able to achieve those through our optimizations. All right, so through fabric formwork, there's a lot of possibilities here in, as I said, low cost and large scale fabrication. And particularly interesting for the properties of curved and organic shapes. The last example that I'd like to highlight is also in an assembly method or a construction method, and this is looking at architectural examples where rather than a single rigid object, we're looking at an assemblage of parts. So this project was presented at SIGGRAPH in SIGGRAPH Asia in 2014 with authors Mario Duce, Daniele Panozzo, myself, Yang Liu, Philippe Bloch, Olga Sorkin-Hornung, and Mark Pauli at ETH Zurich and EPFL and MSR Asia. So the idea with this last project was to reconsider how we do constructions of assemblages of large assemblages of rigid blocks. So when I talk about masonry structures, what I'm referring to are structures that are made out of brick or stone. Historically, this is the most common construction method. This is actually a modern example. This is from 2009, a pagoda in Mumbai, which is an example of an enormous span that was achieved purely by masonry blocks. So this is 90 meters high, spanning 85 meters in the interior domes, using just blocks. So no additional supports, for example, from a steel truss. Now, the assembly of these types of objects, as you might be able to see or understand from looking at the construction site, it's extremely complex to put these structures together. A typical technique is to create supporting formwork, similar to how you would have support structures in 3D prints. So we have a railway bridge in progress in Switzerland here, where you can see an elaborate beam network that's produced first, and then the individual blocks are placed on top until it's finished, and then that's taken away. So this is a temporary support structure, but there's a lot of labor and material that goes into that. On the right, we have another more modern example from 2012. This is from a lab in ETH Zurich, where again, you can see a very elaborate supporting structure that is then simply removed and not used in the permanent form. So we were inspired by a video from this company called United Lock Block, where rather than using a supporting formwork from below, they used chain structures that are in tension to hold the blocks in place. Right, so there are tension chains attached to the blocks, and then after the structure is complete, they take away those chains. So a huge reduction in the amount of material that's needed for these temporary supports. So we were fascinated by this and wanted to see how this could be extended to more general forms. So rather than the arched forms that you see in this example, how could we do something that's more like a general free-form architectural shell? So there's problems both in what the sequencing of the blocks, how should they be laid down, and also are there ways to reduce the labor and even how many chains they have to use. Does it have to be on every block, or can it be on just a subset? So one of the major insights for this work was to use a divide and conquer strategy. So this is actually a historical diagram from cathedral construction. And what's being shown in red is a subset of this groin vaulted structure. So these arched forms in red are actually a very stable structure. Once they're built, they can stand on their own with no additional support needed. So what was commonly done is those would be built first. And once those were built, they could actually act as a formwork or act as a supporting formwork for the remainder of the structure. So as you put in the remainder of the shell, it can benefit from the stability of the initial structure that's laid down. So we were interested in how we could produce those same subsets that are stable within a more general shell. So for freeform shapes, we term these quasi-arches in terms of their stability properties. So in order to find these within general forms, we looked at in depth the way that we actually analyze the stress profiles within structures. So what I'm showing here is an architectural shell with two different stress profiles. So it's known that for any particular structure, for a complex form, there's not just one solution on how the stresses will flow through that structure. There's actually a huge family of solutions. And these are two possible options that both lead to a static equilibrium stable structure. The first has approximately uniform stresses throughout in the blue example. However, in the red example, we've applied different metrics to push the solution towards examples where there are high stresses in very restricted regions of the structure and lower stresses in the remaining areas. And this is done through techniques in sparsity optimization. But the point is that we have these restricted, concentrated regions of high stress. And what you can start to see through this visualization is that you have these continuous areas emerging of high stress where there's these darker red lines. And what that corresponds to is a very similar idea to what we found in the arches, that those concentrated regions can stand with almost no interaction from the areas around them. Right, so we use that as an indicator of where the quasi-arches could be placed. By simply selecting everything above a threshold, doing a flood fill, we could find these candidates for quasi-arches. So here's another example of another shell where, again, we're trying to concentrate these high stress areas into smaller regions and then doing a flood fill within those areas. So given these identifications of quasi-arch areas, we can then use that for a divide and conquer technique of how to approach the assembly. So first we can assemble just the arches within those red regions, so just those quasi-arches. Once that's created, it's a pretty stable structure. And then we can go and create the regions in between each of those the domains within the quasi-arches, which will then benefit from the stability of the surrounding areas, right? So we can go and complete the whole structure like that. So we found that that actually has a huge impact on the total number of chains that are needed to construct these forms. So the other aspect is deciding where the chains actually have to be placed at every state. And so a simple example on that is if you're considering say an arched structure. The completed arch is stable, but if you were to just put in the first 3 blocks, you need extra support. So you could apply a chain on every block, and that would make it stable, but it's actually not required. You could get away with just having 1 and take away the other 2. And you can do this analysis of deciding the minimum number of chains required, again, using techniques in sparsity optimization. And this can be applied to simple structures like this one and also to the more complex shells. So we use those techniques to figure out the minimum number of chains at every state of the construction. So I'll show you a couple examples of what we produced. So here we have just a still of the intermediate stage. This is once the first quasi-arch has been produced. Here's a video showing its construction. So here we had these 3D printed blocks as our test site. So you can see that already there's only 1 or 2 chains that are needed at a time. So there's actually very little extra support required throughout this assembly process. Right, so using that combination of subsets, divide and conquer approaches, and also sparsity optimization, there's very little additional support needed. We also looked at smaller structures for more playful examples. So this is a puzzle sequence where instead of using chains for temporarily supporting objects, you could say instead that this is where the hand needs to be placed for, let's say, a 2-player puzzle. Right, so by giving instructions on assembly, you can tell them where they actually have to hold the puzzle in place so it doesn't collapse while they're building it. And you could also see that the number of players required would be dictated by the maximum number of chains that you need at any point during the construction. Yeah, that's the fun part. All right, so that is an overview of just a few representative projects demonstrating this connection and how to do functional design by pairing mechanics with geometric models and geometric representations, and showing how we can create interesting functional objects with target mechanical and dynamic properties. So we hope that this opens up new ways of looking at design procedures that are accessible while also allowing functionality in the design. So I'd just like to quickly acknowledge the many people that were involved. So these are students that I currently work with, as well as some alumni from Boston University. I'll acknowledge the many talented collaborators from various institutions around the world, as well as funding for these projects, which is also critical. And then I'd like to end with a note that there is an excellent event coming up this summer. Just this is a small advertisement. The Symposium on Computational Fabrication. This is sponsored by the ACM. This is going to be the 5th annual event of SCF, and it's a really fantastic symposium bringing together people from a broad range of domains. It's typically been held at Boston. It was at CMU last year, and it's coming back to the Boston University campus this summer, June 28th to 30th. We have a really excellent lineup of invited speakers. Here's some of the keynotes, and there's more to be confirmed in areas within human-computer interaction, robotics, biology, materials, architecture. So I know we've had presence from Autodesk in the past, so I certainly hope that you consider attending this summer as well. So I'll leave the citations for the papers that I presented up there, and I thank you for your time.
We can open it up to questions if anyone has any. No?
You showed an example of the fabric formwork for an architectural column. Yeah. Did you run into any examples where they actually put in rebar and those sorts of things and made it really structural?
Right. Yes. So yes. So I believe that within structural engineering, architectural labs, that they have been experimenting with how to integrate rebar within the cast. This is something that, yeah, we're certainly interested in learning how to do that as an integrated process. So there's definitely challenges in how to how the tailoring would accommodate that. But yeah, I think it's definitely an important future work to look into. Yeah.
Other questions? Well, thank you, Emily, so much for presenting today, and I think that's a wrap. Have a great day.